VLSos here. This is a video lesson on implicit differentiation. First, let's look at a function and take a derivative that is familiar. Y equals the cotangent of 2 to the x. We are familiar with taking derivatives, often given the notation dy over dx. And what this notation means is take the derivative of y, which we assume then is an equation solved for y that we're given, with respects to x. So we are assuming that the equation that we're given solved for y has that one variable x in it. So taking the derivative with respects to x is just a matter of applying the derivative properties to this particular function. This is a composite function. The derivative of cotangent is cosecant squared of, composed with, 2 to the x. But then a composite function, we need to apply the chain rule and multiply by the derivative of the inside function. In this case, we have an exponential function, so the derivative of it is 2 to the x itself times the natural log of its base, 2. This is explicit differentiation because we're given a function to take the derivative of that is solved for that variable, and it's in terms of the variable that we're expected to find the derivative with respects to. We don't have to start this way. Explicit differentiation is straightforward, but not the only way we can take a derivative. With a function such as this, y to the 4th minus cosecant of e to the x is equal to 4 to the y. We can see we might be confused if we're asked to find the derivative of y with respects to x, because y is not solved for, and solving for y in this case, if we could manage the algebra, would produce probably more than one equation, because undoing this even power would have to include both the positive and negative versions. So what if we were asked to find the derivative of this? We could, with notation, put d over dx as that instruction, find the derivative of what we have here in parentheses with respects to x. We can do it. We don't have to solve for y first. What we're going to do is we're going to take this derivative, and we call that implicit differentiation. Here's how to think when asked to take a derivative implicitly. We're going to treat all other variables as functions of the variable we are differentiating with respect to and apply the chain rule. This is what you need to remember, but what does that mean? Well, the notation tells us what the variable that we are differentiating with respects to. It's in the denominator, in this case it's x. So we're going to treat all other variables, and the only other one is y, as functions of x, and then apply the chain rule when appropriate. What does that look like? Let's do it. The derivative of y to the fourth is 4y cubed, power rule. But we're not differentiating with respect to y, we're differentiating with respect to x. So I need to consider that y is a function of x as if the y to the fourth was a composite function. Again, y to the fourth we're thinking as a composite function, the fourth power function composed with y, which is itself a function of x. So I continue to take its derivative by applying a chain rule, by multiplying by the derivative of y with respect to x. Now, dy over dx is as far as I can take it. Dy over dx stands for a derivative, but there's no other number or mathematics that I can do. I've finished taking the derivative of y to the fourth. Moving on to the next term, the derivative of negative cosecant e to the x, which is a composite function, but it's composed ultimately with the variable that I'm taking the derivative with respect to. So there's no extra thinking involved in taking the derivative of just this expression. The derivative of cosecant is cosecant times cotangent. Or in this case, I am going to take the derivative, it's negative cosecant composed with e to the x times cotangent also composed with e to the x. Now for a chain rule, I need to multiply the derivative of cosecant by the derivative of what it's composed with. And the derivative of e to the x is itself. Continuing, I'm going to equal the derivative of 4 to the y. With respect to x, again, I'm going to consider y as a function of x and apply the chain rule. First, I have to take the derivative of the exponential function, 4 to the y, which is itself, times the natural log of the base, in this case 4. Now it's time to apply the chain rule and multiply by the derivative of what 4 to the y is composed with, and that gives me a dy over dx. I've taken the derivative implicitly. I was able to do it right away without solving for anything. Notice that I do have the dy over dx. It's in two places. Some problems would require solving for the dy over dx. And in this case, I would have to get the terms that contain it on one side and factor it out so that it's in one place. Let's practice one more. I'm asked to find dy over d theta, given the equation y squared plus e to the 4z is equal to n times m. Look how sophisticated this can get, but it's not difficult. I have an equation that has 1, 2, 3, 4 different variables in it. And the variable that I am asked to differentiate with respects to isn't even in the equation that I'm given. That's okay. I can go with this thinking and take the derivative implicitly. When I do, I'm going to take the derivative of this first term. That's 2y. But I'm going to think of the squaring function composed with a function for theta. So I need to chain rule out dy with respects to theta and continue to take the derivative. E to the 4z is a exponential function base e, which is itself e to the 4z. With a chain rule, to multiply by what composes e to the 4z, and the derivative of 4z is 4. But I need a second chain rule because I'm thinking of z as a function of theta. So I multiply by dz over d theta is equal to a product rule n and m both are being thought of as functions of theta. So I'm going to apply a product rule and then the appropriate chain rules when I do. The product rule is the derivative of n, which is 1, but then chain rule times the derivative of n with respects to theta. Continuing the product rule times m. And then plus n, the first function, times the derivative of m, which is 1, but we're thinking of m as a function of theta, so I need to apply a chain rule, dm over d theta. I have an equation in which I took the derivative of y with respects to theta, and I have the derivative of y in this one place. But it's inside of an equation with other terms and other math going on. So if I'm asked to find dy over d theta, I need to solve for that piece of it. And I can solve for it by subtracting this term and then dividing by 2y to get the dy over d theta by itself. When I do that, I'll have dy over d theta is equal to this other side where I'm going to ignore the multiplications by 1. So it is dn over d theta times m plus n times dm over d theta. And then I'm going to subtract this term, e to the 4z times 4 times dz over d theta, which will get the 2y dy over d theta on one side, and then to get this by itself, I divide by 2y. It was a little complicated, but you can see it can be done. Implicit differentiation allows you to differentiate immediately, it allows you to differentiate anything, and it allows you to differentiate with respects to anything, even if you don't have that variable in your original expression or equation.